Okay, now we get to an application of tangent lines that allows us to approximate a function using a line. So for example, let's say we have a function that looks like this maybe, and I'll try to exaggerate it as the best I can. A function that looks like that, and we have some point, some x value a, and clearly there's a point here. Then what we could do is whenever your x is near a, you can see that you'd get a tangent line that might look something like this. So whenever x is near a, your function, let's call the black graph f of x, let's call the red graph y, or f of x, that black function is approximately equal to the red function y, specifically when x is near a. Now the key here is that this could be any type of function, any type of curve. However, it can be approximated, very interestingly, it can be approximated by this y function, which is always a line. In fact, it's the tangent line. So a function can be approximated, the outputs of a function can be approximated by a simple line. Okay? So if we can calculate the equation of the tangent line, we have the approximate output of this function as long as we're near that point in question. For example, the tangent line over here would be different. You'd have a different tangent line. So at this point, B, you would have a different approximation for the function than you did at the point A. Okay, so the approximation that you'd use is dependent on the x value that you're interested in. But calculating outputs of a line like y equals mx plus b is much easier than perhaps the various types of curves or functions you could see in general. So here I want to find a linear approximation of the function x squared at 3. So what I need is, this is the same question as find the equation of the tangent line at x equals 3. And if x is 3 for this function, y is 9. So we have the ordered pair of 3, 9. So in order to do that, I clearly need the slope of the tangent line. So the m that we'll use is the slope of the tangent line, which is 2x. And precisely, the slope of the tangent line happens at x equals 3. So that'd be f prime of 3, which would be 2 times 3. And the slope we would use would be 6. So the tangent line equation is of the form y equals mx plus b. We know that m is 6. We know that an x that we can use on that tangent line is 3. We know that y we could use is 9 plus b. So b would be 9 minus 18, which is negative 9. So the equation of the tangent line is y equals 6x minus 9. And the neat thing is, the original function f of x is approximately equal to 6x minus 9 when x is near 3, the original value. Okay, so if you drew a picture of this, x squared looks like this, of course, on the right side here. And when x is 3, we've got a tangent line that looks like this. Whenever x is near 3, the tangent line is very close to the function, the original function x squared. So x squared is f of x. X squared is approximately equal to 6x minus 9 when x is near 3. So if we use that reasoning, so now let's answer another question with this. So now we know that the x squared function can be approximated by the 6x minus 9 function when x is near 3. So if I want to approximate 3.001 squared, that would be like our x value, right? X squared. So the approximation of that would be approximately 6 times 3.001 minus 9. Well, that equals 18.006 minus 9, which is equal to 9.006. So this is approximately, this is an approximation for 3.001 squared. Now, if you calculate 3.001 squared, you actually get 9.006001. So you can see how close these are. And this is very easy to calculate, right? It's just a linear function that you plug it in. And you may use a calculator to get it, but it's much easier to calculate the output of a linear function, a linear approximation, than it is maybe to calculate the output of this function here. Now this example may not illustrate it very well, but that's what this is good for. If your function is rather complex, you may want to calculate outputs using the linear approximation because it's pretty easy to do.